Welcome to CyberXplain channel. Today we are going to discuss unmasking AI's dark side, practical LLM threat modeling vertical bar CyberXplain. Hey everyone, welcome back to CyberXplain. Today, we are diving into a super hot topic, securing our amazing large language models. These AI applications are transforming how we work and interact, but with great power comes great responsibility, right? Just like any new tech, they introduce unique security challenges we need to understand and tackle head-on. Ignoring these could lead to anything from data breaches to reputational damage, and trust me, nobody wants that. Think about all those customer-facing chatbots or internal tools using LLMs. A single vulnerability could be a huge problem. So, let's get proactive and learn how to protect them from the get-go. Before we jump into LLMs specifically, let's quickly chat about what threat modeling even is. Simply put, it's a structured way to identify, categorize, and prioritize potential threats to your system. Imagine you are building a fortress. You wouldn't just build walls and hope for the best, right? You'd think about who might attack, how they'd get in, and what they'd want to steal. That's exactly what we do in cybersecurity. It's about asking what could go wrong, and then figuring out what can we do about it. It helps us shift from a reactive mindset to a proactive one, which is always a win. You might be wondering, why can't we just add security later? Well, for LLMs, and really any software, bolting on security at the end is like trying to put a parachute on after you've jumped out of the plane. It's often more expensive, less effective, and can significantly delay your product launch. By integrating threat modeling into the early stages of development, when you're still designing your LLM application's architecture, you can catch fundamental flaws before they're coded in. This approach is called security by design, and it's particularly crucial for AI systems given their complex, evolving nature and often sensitive data handling. It truly saves headaches and heartaches down the line. One of the most popular and foundational frameworks for threat modeling is STRIDE. It's an acronym that helps us categorize and think about different types of threats, ensuring we don't miss anything critical. STRIDE stands for Spoofing, Tampering, Repudiation, Information Disclosure, Denial of Service, and Elevation of Privilege. Each of these represents a different angle an attacker might take to compromise your system. We'll walk through each of these and see how they apply specifically to the world of LLMs. It's a great mental checklist to start with. Let's kick off with S for spoofing. In the context of LLMs, spoofing means an attacker successfully impersonates a legitimate user, another service, or even the LLM itself. Think about a prompt injection attack where a malicious user tricks your LLM into believing they have certain permissions or that it should ignore its safety guidelines. Or perhaps an attacker could spoof the identity of your internal API, making the LLM send sensitive data to the wrong place. This could lead to unauthorized access or data exfiltration. Authentication and strong input validation are key defenses here. Next up is T for tampering. This threat is all about unauthorized modification of data, either in transit or at rest. For LLMs, this could mean an attacker altering the prompts sent to the model, or even the responses received from it, before they reach the intended recipient. Imagine a scenario where a user asks for financial advice, and an attacker intercepts the LLM's helpful response, inserting malicious instructions instead. Or, even more subtly, tampering with the training data itself, a supply chain attack on your model's knowledge base. Ensuring data integrity and secure communication channels are vital. Then we have R for repudiation. This is when a user or system entity can deny having performed an action, and there's no way to prove otherwise. In an LLM context, think about an administrator who uses an LLM-powered tool to make a critical configuration change. If logging is insufficient or easily manipulated, that administrator could later deny making the change, leaving no audit trail. This is particularly problematic in regulated industries or for sensitive operations. Robust logging, immutable audit trails, and proper digital signatures where applicable are our best friends against repudiation. I stands for information disclosure, and it's a big one for LLMs. This is when sensitive data is exposed to unauthorized individuals. LLMs can inadvertently reveal confidential training data, internal system prompts, or even user PII if not properly constrained. Imagine an LLM that, through a clever prompt, leaks customer names, payment details, or proprietary business strategies it was trained on. This is a classic data breach scenario, often achieved through data extraction or model inversion attacks. Robust access controls, data anonymization, and strict output filtering are non-negotiable here. Next, D for denial of service. This threat aims to make your LLM application unavailable to legitimate users. For LLMs, a DOS attack could involve flooding the service with an excessive number of complex or computationally expensive prompts, consuming all its resources. Think about an attacker repeatedly sending queries that force the LLM to generate extremely long responses or perform iterative tasks, grinding your service to a halt. This could also be a supply chain DOS, where a dependency for your LLM service becomes unavailable. Implementing rate limiting, robust load balancing, and efficient resource management are crucial for keeping your LLM online and responsive. Finally, E for elevation of privilege. This is when an attacker gains higher access, rights, or capabilities than they're supposed to have. In an LLM context, a clever prompt injection might trick the LLM into executing commands or accessing data that it shouldn't normally be able to, effectively escalating its privileges within the broader system. For example, if your LLM has access to a backend API with elevated permissions, a malicious user could craft a prompt to make the LLM call that API with parameters leading to unauthorized actions. Strong isolation between the LLM and sensitive system components, along with careful permission management, is absolutely vital. While Stride helps us categorize threats, frameworks like PASTA give us a structured process to conduct threat modeling from start to finish. PASTA stands for Process for Attack Simulation and Threat Analysis, and it's a risk-centric methodology. Instead of just listing threats, PASTA focuses on understanding the business impact and simulating how an attacker might exploit vulnerabilities. It's a 7-step framework that goes deep into the application and its context. This makes it particularly useful for complex systems like LLM applications where understanding the full attack surface is crucial. It's a more comprehensive approach. The first step in PASTA is all about defining your scope. Before you can secure anything, you need to know exactly what you are trying to protect. For an LLM application, this means identifying which components are in scope. Is it just the LLM itself, or also the user interface, the data pipelines, the backend APIs it interacts with, and the hosting infrastructure? What are the key functionalities? What data does it process or store? Clearly outlining these boundaries helps you focus your efforts and ensures you don't waste time on irrelevant areas or, worse, miss critical parts. Be as granular as possible. Once you know what's in scope, the next PASTA step is to understand the business impact of potential threats. This isn't just a technical exercise, it's about connecting security to the real-world consequences for your organization. What's the financial loss if customer data is leaked? What's the reputational damage if your chatbot starts generating harmful content? What's the operational impact if your LLM service goes down for an hour or a day? Prioritizing threats based on their potential business impact helps you allocate resources effectively, ensuring you focus on the most critical risks first. It's about why this matters to the business. Now we get technical with application decomposition. This step involves breaking down your LLM application into its constituent parts, understanding its architecture, data flows, and trust boundaries. You'd typically create diagrams like data flow diagrams, DFDs, to visualize how data moves between components, where trust is established, and where potential entry points or points of failure exist. For an LLM, this might include the user interface, the API gateway, the LLM inference engine, databases, and any external services. This granular view helps identify distinct attack surfaces and threat vectors more clearly. Think of it like disassembling an engine to understand how each part works. With your application decomposed, step 4 is threat analysis. This is where we brainstorm potential threats using frameworks like Stride, which we just discussed, or even the OWASP top 10 for LLMs. For each component and data flow identified in the decomposition step, you'd ask, what are the possible Stride threats here? For example, for the input to your LLM, you'd consider spoofing, prompt injection, tampering, and information disclosure. You'd generate a comprehensive list of potential threats, without worrying about prioritization just yet. This step is about casting a wide net to capture every possible bad thing that could happen. Now that we have a list of potential threats, PASTA's fifth step, vulnerability analysis, focuses on finding specific weaknesses in your LLM application that an attacker could exploit to realize those threats. This is where you identify actual flaws in your design, implementation, or configuration. Are there weak input sanitization routines? Are API keys hard-coded? Is the LLM overprivileged? Does it lack proper guardrails for its output? This involves reviewing code, configurations, and documentation. You might even use automated scanning tools, but a human expert's eye for LLM-specific vulnerabilities is often irreplaceable here. This is about identifying the holes in the fence. With threats and vulnerabilities identified, step 6, attack modeling, is where we put on our hacker hats. This step involves simulating how an attacker might combine vulnerabilities to launch an attack. You create attack trees or attack graphs to visualize the steps an attacker would take from initial access to achieving their objective. For an LLM, this might involve chaining a prompt injection to gain control, then leveraging an overprivileged LLM role to access sensitive data, and finally exfiltrating it. This step helps uncover complex, multi-stage attacks that might not be obvious when looking at individual vulnerabilities. It's about seeing the whole attack chain. Finally, PASTA Step 7 ties it all together with risk and impact analysis. This is where you prioritize the identified threats and vulnerabilities based on their likelihood of occurrence and their potential business impact. Remember our business impact analysis from Step 2. Now we combine that with how easy or hard it is to execute a successful attack. This helps you decide which mitigations to implement first. Not every vulnerability needs a nuclear-level defense. Sometimes, a simple fix is enough if the risk is low. This step ensures you are spending your security budget and effort wisely, focusing on the biggest bang for your buck. Now, let's zoom in on LLM architectures. To threat model effectively, you need to understand the typical components involved. At a high level, you'll usually have a user interface, like a chatbot frontend, an API gateway that routes requests, the actual LLM service itself, whether it's an API call to OpenAI, Anthropic, or your own deployed model, a vector database for RAG, retrieval augmented generation, and possibly other backend services for business logic or data storage. Each of these components, and the connections between them, represents a potential attack surface. Mapping these out is critical for our decomposition step in PASTA or simply applying Stride effectively. Understanding the data flow is paramount for LLM threat modeling. Data flows from the user, through your application, to the LLM and often back again. But it's more complex than that. There's user input data, system prompts, or guardrail prompts, potentially sensitive business data retrieved from a vector database for RAG, the LLM's generated response, and any subsequent data logged or stored. Each transition point is a potential spot for tampering or disclosure. For instance, is the data encrypted in transit? Is it sanitized before hitting the LLM? Is the LLM's output filtered before it reaches the user? These are crucial questions to ask at every stage of the data's journey. When we talk about identifying LLM vulnerabilities, we are not just looking for traditional web app flaws anymore, though those can still exist. We are focusing on issues unique to how LLMs process information and interact. You've probably heard of prompt injection, but there's a whole spectrum of risks. Think about data leakage through sensitive training data, insecure output handling, or even supply chain vulnerabilities introduced by using third-party models or fine-tuning datasets. This requires a new mindset for security professionals, understanding how the AI itself can be manipulated or misused. We need to go beyond the typical SQL injection mindset. Prompt injection is arguably the most famous LLM vulnerability. It occurs when an attacker manipulates the LLM's behavior by sending specially crafted input prompts, often overriding system instructions or making the model do things it shouldn't. This can lead to information disclosure, unauthorized actions, or even a form of denial of service. Detecting it often involves monitoring LLM outputs for unusual patterns or attempts to bypass instructions. Mitigation strategies include robust input validation, using a separate moderation model to filter malicious prompts, implementing privilege separation for the LLM's actions, and careful prompt engineering to make system instructions robust. Don't trust user input near your LLM. Next up, insecure output handling. This happens when the LLM generates malicious or risky content that's not properly validated or sanitized before being displayed to users or used by other systems. Imagine an LLM that, through a prompt injection or simply a flawed generation, outputs JavaScript code that then executes in a user's browser, leading to excesses. Or perhaps it generates SQL code that could be injected into a database if the downstream system blindly uses the LLM's output. Mitigation involves rigorous output filtering and sanitization, ensuring that anything the LLM produces is treated as untested and scrubbed clean before being integrated into other systems or displayed. Always validate what comes out of the LLM. Training data poisoning is a sneaky one. This is where an attacker subtly introduces malicious data into the LLM's training set, causing the model to learn and reproduce biased, incorrect, or harmful behaviors. This can lead to backdoors in the model, where specific prompts trigger unwanted actions, or simply degrade its performance and reliability. Think about a targeted attack on a publicly available dataset that's later used to fine-tune your proprietary LLM. Detecting this is incredibly hard, often requiring continuous monitoring of model behavior for deviations. Mitigation focuses on rigorous data provenance, verification of training data sources, and anomaly detection during training and inference. Trust your data source, but verify. We touched on DOS earlier with Stride, but let's look at model denial of service specifically. This happens when an attacker exhausts the LLM's computational resources, making it unavailable or extremely slow for legitimate users. This isn't just about simple request flooding, it can involve crafting prompts that are disproportionately expensive to process. For example, a prompt asking the LLM to write a 10,000-word story in Latin or perform complex recursive reasoning tasks. Detection involves monitoring inference times, resource utilization, CPU-GPU, and unusual request patterns. Mitigation includes robust rate limiting, request quotas, enforcing response length limits, and using optimized, efficient models. Supply chain vulnerabilities are a huge concern for LLMs, just like they are for traditional software. This covers everything from the foundational models you use, are they secure and trustworthy, to the datasets they were trained on, to the libraries and frameworks you use to integrate them. If any part of this chain is compromised, say, a dependency with a backdoor, or a fine-tuning dataset with hidden malicious instructions, your entire LLM application could be at risk. Remember the SolarWinds attack pattern? It's similar here. Detection requires robust software supply chain security practices. Mitigation involves thorough vendor vetting, integrity checks on models' datasets, and using trusted registries and pipelines. You are only as strong as your weakest link. Now that we've identified threats and vulnerabilities, how do we fix them? Developing mitigation strategies for LLMs follows some general security principles. First, assume breach design defenses as if an attacker will eventually get in. Second, apply the principle of least privilege. Give your LLM only the permissions it absolutely needs and no more. Third, implement defense in depth, layering multiple security controls. Think about input validation, output sanitization, robust access controls, continuous monitoring, and strict logging. It's about creating multiple hurdles for an attacker to overcome. Don't rely on a single magic bullet, because there isn't one. Let's put this all into practice with a quick case study, a customer-facing chatbot. Imagine this bot helps users with account queries and occasionally accesses their personal info. Using Pasta, we'd start by defining the scope: UI, LLM service, CRM API, auth service. Business impact: high for PII leak, medium for DOS. Decomposition would show data flowing from user, UI, API gateway, LLM, CRM. Now, for threats. Prompt injection, spoofing, is huge here, potentially leading to unauthorized data access. Insecure output handling could lead to sensitive data being displayed incorrectly. Training data poisoning could make the bot give bad advice. We'd model attacks, like prompt inject to extract PII, and then prioritize based on risk. For this chatbot, PII extraction would be top priority. Building on our chatbot example, how do we defend it? For prompt injection, we'd implement strong input validation at the API gateway and crucially, use a separate, smaller safety LLM to check user prompts for malicious intent * before * they hit the main LLM. Output sanitization is key, ensuring any generated responses are stripped of harmful code before display. To prevent information disclosure, the LLM itself should only have read-only, least privileged access to the CRM data, and we'd enforce strict data redaction on its output. We'd also monitor for unusual CRM access patterns initiated by the LLM. It's a layered defense, combining technical controls with architectural choices and continuous monitoring. Here's the kicker: threat modeling isn't a one-and-done activity. Especially with LLMs, which are constantly evolving, you need to treat it as a continuous process. New vulnerabilities are discovered, models are updated, and your application's functionality might change. This means regularly reviewing your threat models, updating them with new information, and implementing continuous monitoring of your LLM application's behavior. Look for anomalous outputs, unusual API calls, or spikes in resource usage. Integrating security into your DevOps pipeline and making threat modeling a regular part of your development sprints is how you stay ahead in the dynamic world of AI security. Stay vigilant. Alright, we've covered a lot today. From the foundational Stride and Pasta frameworks to the unique threats facing LLMs like prompt injection and training data poisoning. Remember, securing your AI applications isn't just a technical task, it's about understanding business impact, thinking like an attacker, and building defense in depth. By actively engaging in threat modeling, you are not just reacting to incidents, you are proactively building robust, resilient, and trustworthy AI systems. Keep learning, keep questioning, and keep making the digital world a safer place. Thanks for joining me on CyberXplain, and I'll see you next time. Thanks for watching. Subscribe to the CyberXplain channel. See you on the next video.